Hi everyone, welcome to the course on measurement and instrumentation, and we are discussing the second module of this course where we are talking about analog meters, and this is the fourth lecture in this analog meters where we are discussing about different classification of analog meters. So, if you follow from the previous class, we have talked about different ways to classify the analog meters, including the classification based on quantity which it measures, based on the function that it does, okay, and based on the method which is used for comparing the measured values like direct measurement, indirect measurement, or say comparison kind of instruments, okay. Then we also talked about based on the principle of operation, based on the construction and the movement, which is our discussion for today, and based on the nature of signals that we have to still discuss, okay. Based on the damping method, of course, we will talk about in brief, okay, but today we are going to talk about classification of analog meters based on the construction and the moving part in that particular meter. So, if you see, that can be classified under different heads like moving coil, moving iron, electrodynamic. So, if you are talking about electrodynamic, you also have electrostatic kind of devices, and then we have induction type of analog meters, okay. But if you see these names, we have already talked about these names when we talked about analog meters based on different principle of operation, as you can see. So, if you remember in the previous class when we were talking about different principle of operation, we have minutely observed the principle behind working of this moving coil, for example, or moving iron, okay. But in today's class, we will see that how their construction differs and how this difference in the construction actually have impact on the measurement tool, okay. So, let's discuss in little detail. Okay. So, as I have mentioned that we are discussing about analog instrument which are based on or differences which is based on the construction and the moving part. Okay. So, this analog instrument use a moving system whose motion depends on the electrical quantity which is under measurement. Okay. These instruments differ by how the moving system is built and what causes the pointer to move, okay. Each type of instrument that you have seen utilizes specific electromagnetic principle for measurement, but we will see that we can have other ways of measurement, say based on charge like in electrostatic systems, okay. So, we will mostly, because all the instrument that we are going to discuss is mostly based on magnetic system. So, what we will see is mostly the difference in the construction of systems which is based on magnetic or electromagnetic system, but then it is important to discuss the electrostatic kind of instrument also. So, that is why we have included that as fifth point. So, basically if you see, these are not different type of analog instrument based on construction, but what we will see basically is that how this construction is different, because all of these are mostly based on magnetic effect that we have already seen, okay. But what we are interested in is how the construction of these instruments or the pointer or the moving element is different as compared to each other, and what effect it causes on the measurand, okay. The measurand here is, say, for example, current, it can be voltage or even a power in terms of, say, a watt or say energy meters, okay. So, let us first talk about the moving coil kind of instrument, which is, of course, we have seen that it is also known as PMMC kind of instrument, which is a permanent magnet. So, whenever I am using the word moving coil, please note that I want to say a permanent magnet moving coil, okay. Permanent magnet moving coil. So, in short, sometime it is called moving coil instrument, okay, but it is basically a permanent magnet moving coil system. So, because this permanent magnet is a integral part of the basic construction, okay. So, since we are discussing the instrument based on the construction and how the moving part differs in this. So, let us talk about this PMMC tool which has a permanent magnet, okay. So we'll see how a permanent magnet looks like. Of course, we'll talk about these instruments construction in more detail in coming classes, but right now I am giving you overall picture of how this instrument looks like. Okay, so you have a permanent magnet in the system, then we have a soft iron core. Okay, then you have moving part, we'll see what this moving coil is, and then you have other systems like spindle and pointer, then control springs, damping system. We'll talk about that, these things in coming weeks. Okay, let's see from the construction point of view, like it has a permanent magnet. So a permanent magnet basically in this moving coil or PMMC tool looks like kind of U shape. Okay, and it is used to provide a steady magnetic field. Okay, so if you see the construction, you have a permanent magnet. Okay, so in like you have U-shaped magnet, for example, like so you have magnetic systems such as like this, say this is a north pole and say this is a south pole of the magnet. Okay, and in this area you have a say a cylinder. Okay, you have a cylinder like this which is called the core, and this core is made up of say soft iron. All right. So this soft iron basically, you know that we have discussed this in detail, that this soft magnetic materials, okay, they magnetize very easily, but they demagnetize also very easily. Okay, so this core basically makes the magnetic field uniform and increase the sensitivity of this particular device. Okay, then you have a moving coil in this, which is say wrapped on top of say some rectangular block. Okay, something like this. Okay, so it is wrapped on this, say like this. All right, or in better way, if you see, this is your it is like this. Okay, and this rectangular block that you are seeing is basically is made up of say aluminum. All right, and this wire is say made up of copper. Okay, so this insulated copper wire is wrapped like this, and so say the current which is under measurement flows through this, and it flows like this in the wire. Okay, now this coil is free to rotate between the magnetic poles. So basically what arrangement you have is like this. So you have this say magnetic system. Okay, so say you have this kind of system. Okay, in between you have this core, and then you have this aluminum frame. Okay, and on that you have this wire. Okay, so this system is lying here. Okay, so I am considering it separately, but you visualize that this is placed over here. Okay, now you have this coil placed in this field. What happen is you have current flowing like this in this wire downward. Okay, and you have current flowing like this, so means upward in this wire. Okay, and as usual, you have this magnetic line of force from this north pole to south pole. Okay, you have this flux lines. All right, you have this flux lines. Okay, so what is happening basically in this case, you have current flowing like this, and here you have current flowing like in this direction. Okay, the direction of force, since this is a current carrying coil lying in a magnetic area, okay, so some force is acting on this coil. Okay, and the direction of the force can be given by Fleming's left hand rule. Okay, so you have current flowing like this, flux line like this. So if you see, you have flux line like this and current like this. So you have a force like coming upward. Okay, so you have a force like this. Okay, and just opposite force is acting on the other side, because the current direction is just opposite what is flowing over here. Okay, because of this difference in the applied force or experienced force, what will happen is this coil will start rotating, because this is kind of hinged at this point, and basically what you are exerting is a torque. All right. So of course, we will derive this torque equation and other things in the coming weeks. So the construction is like this, so that you have this coil moving in this magnetic field when a current starts flowing through this coil. Okay. Now you have a spindle and pointer system to support this movement. We will discuss that when we will talk about this PMMC tool in more detail. But even for a small force, you will see that this coil will start rotating, and it can rotate ideally for infinite time if you do not have a controlling mechanism. Okay, and it can oscillate also if you do not have a damping mechanism. Okay, so all the tool that we are going to see will have controlling springs and different damping system. We will discuss about the specific damping system for the that particular analog tool when we will talk about those instruments in more detail. Okay, but this is how construction of a moving coil system looks like. Okay, going ahead, we have another class of analog instrument which are known as moving iron kind of instrument. Okay, and the construction of moving iron kind of instrument is little bit even simpler as compared to what we have just experienced for PMMC tool. So you have a coil, of course current carrying coil, and then you have soft iron pieces, and then further ahead you have pointer and scale similar to what we have seen there, and then other parts include a control mechanism and a damping mechanism for the similar purpose. Okay, so you have a stationary coil of many turns, again made up of insulated copper wire. This copper wire carries the current or the current proportional to the voltage, which has to be measured if you are using it as a voltmeter. Okay, the coil produces a magnetic field when current flows through it. Okay, now you have soft iron piece. Okay, so the idea is you have a coil, okay, which is wrapped over here, and say there is a current which is flowing through it. Okay, now you will bring soft iron. Again, if you remember, soft iron can be magnetized very easily, and it can again be demagnetized very easily. Okay, now when you bring this soft magnet to near to this coil, a field will be, or this soft iron will be magnetized. Okay, this will be magnetized. Okay, now when this is magnetized, and if you try to bring this near, okay, near to this, what will happen, say if you attach a pointer to this, what will happen is this coil will try to repel this. Okay, because of that, what will happen, this pointer will have certain movement. If you remember, we have talked about this. Okay. So, based on what kind of principle it is using, you have either attraction type or repulsion type. So, when you are bringing this magnet, depending on its polarity, it can attract or it can repel. Okay. We will see what it means. Okay. But when you try to bring this near to this, if say for example, if it is attracting, okay, this pointer will have certain movement. All right. So, based on that movement, you will have a measurement of the say if you are trying to measure current or if you are trying to measure the voltage. Fine. So, that can be measured. All right. So, what we are trying right now is just to understand this. Okay. If you understand the basic principle, okay, once it is very clear that what kind of tool it is, okay, you can decide if it is attraction type or repulsion type. But let us quickly see what is attraction type and what is repulsion type, because there is a little bit difference in the construction. Okay. So, in the attraction type of moving iron or MI kind of instrument, okay, a stationary coil is wound on a non-magnetic former that we have just discussed. Okay. A soft iron vane, which is nothing but a flat piece that we have seen, is mounted near the open end of the coil. Okay. Now, this iron vane, when it is attached to the spindle which carries the pointer, we will see the spindle system later on. Okay. Now, when current flows through the coil, it creates a field and the soft iron piece is actually attracted into the coil where the field is stronger. Okay. So, you have this coil and you have this magnet. So, when you pass this current, okay, this iron is getting magnetized and it is getting attracted. Okay. Right. So, as we have just discussed that depending on this attraction, this pointer will be deflected. Okay. So, if you see this attraction type of instrument, you have only one magnetic vane, okay, or one flat piece of iron, this flat piece of iron or soft iron basically. Okay. Now, let us see what is repulsion type of instrument. So, in the repulsion type of instrument, it has basically two soft iron pieces. Now, in these two soft pieces, so let us try to again understand this, okay, because I have already given you an idea of attraction and repulsion. Okay. Now, you have say this current flowing. Okay. Now, you have now two magnetic pieces. Okay. Both are getting magnetized. Okay. Now, I have fixed one iron piece, say I am calling this 1, calling this 2. Okay. Now, this is fixed when both are magnetized. So, this is say south pole or north pole or south pole and north pole. Okay. This is getting repelled by this one. Okay. So, since both are placed in a common coil, okay, the movable iron piece is attached to say pointer and say any repulsion in this will be recorded as a pointer movement. Okay. So, when current flows through the coil similar to the other one, both iron pieces become magnetized with the same polarity, and due to like poles basically they repel each other. Okay. The movable iron piece moves away, causing pointer deflection. All right. So, again you have the pointer and a scale, which again is a matter of discussion that we will discuss in the later part of this course, and again that will be discussed along with the control mechanism and damping mechanism, because this too is very important or crucial part for any kind of instrument. All right. Then third kind of instrument that we have seen in the previous class also is the electrodynamic kind of instrument. Okay. We have seen that these electrodynamic instruments work on the principle of interaction between two magnetic fields, one produced by a fixed coil and the other produced by the moving coil. Okay. The construction of this instrument is quite differs from the PMMC and moving iron kind of tools. Okay. The electrodynamic instrument mainly consists of fixed coil, which is also known as the field coil, a moving coil, and a pointer, okay, similar to the others, okay, and you have control mechanism, damping mechanism, and a moving system support, okay. So basically the construction is very simple. Two stationary coil are mounted close to each other and are connected in series, okay. So say you have, say, these two coils, okay, say I am calling this, say, coil 1 and this is coil 2, all right. So these two are the stationary coils or the field coils which are mounted close to each other and connected in series. Now these are made up of thick copper wires to carry the main current, especially in case of the current meters or the ammeters or the power meters, okay. Now this coil produces magnetic field when current flows through them, okay, and they are mounted on a non-magnetic frame very similar to the others, okay, to avoid any kind of interferences, okay. Now a light movable coil made up of a fine wire is mounted on a pivoted spindle, okay, or for the time being let us consider this like you have, say, this fixed coil, okay. Now this is, say, moving coil, okay. So this is coil 1, coil 2 and the moving coil, all right. Now this moving coil is a very light movable coil which is made up of, say, fine wires of, say, copper only, okay, and this is mounted somewhere here, okay. So it is placed within the magnetic field which is produced by the field coils, okay. Now the moving coil carries a current that produces its own magnetic field, okay. Now the interaction between the magnetic field of the fixed coil and the moving coil produces a deflecting torque, okay. We have seen that why the torque is produced in case of PMMC, why the torque is produced in the moving iron, and why the torque is getting produced in the electrodynamic kind of instrument, okay. So the interaction between the magnetic fields of the two coils, the field coil and the moving coil, actually is the responsible thing for generation of the deflecting torque, okay. Now the pointer is attached to the spindle and it moves over a calibrated scale. We will discuss about the scale and other things of this electrodynamic instrument when we will discuss the torque equation and other parts, okay. Again, the control mechanism and damping mechanism are important or a crucial area of this electrodynamic kind of instruments, okay. Then we have a induction kind of instrument, okay. These induction instruments work on the principle of electromagnetic induction, the same principle which is used in the transformers, okay. They operate again only on AC because electromagnetic induction require a changing magnetic field to induce currents which is known as the eddy currents, okay. Now when AC current flows through the coil, alternating magnetic fluxes are produced, okay, and these fluxes induce eddy currents in a metallic disc, okay. The interaction between fluxes and eddy currents produces a driving torque which we are not going to discuss right now, but we will talk about it if we will talk about the induction type of instrument. But because of the time constant, maybe we will not be discussing much on induction type of instrument, but will focus more on PMMC, moving iron and electrodynamic kind of instrument. But the construction of this instrument is very simple. So you have a magnetic system, a moving element, a braking system, control system similar to the other systems that we have seen, okay. The magnetic system of this induction type of instrument is basically two electromagnets, okay. So these are basically iron cores with coils and they are mostly known as shunt and series magnets, okay. So these two electromagnets generate alternating magnetic fluxes, and the alternating magnetic fluxes will have a phase displacement between them, okay. And these fluxes induces the eddy currents in the moving element, and this moving element is mostly metallic disc, okay. Now these two fluxes, say phi 1 and phi 2, which is basically the series magnetic flux and shunt magnetic flux, are proportional to the load current and proportional to the supply voltage respectively. Okay. But of course, the shunt magnetic flux, which is proportional to the supply voltage, will be shifted in phase. Okay. The moving element is basically a light aluminum or a copper disc. Okay. The disc is again mounted on a spindle which can rotate. Okay. And the alternating fluxes induces eddy currents in the disc which interact with the magnetic fluxes, and because of this, torque is produced. All right. So apart from this, you have a braking system, a control system, and a bearing system in this induction type of instruments. Okay. Then you have altogether a different category of instrument, which is the electrostatic type of instrument. Okay. We will see part of this electrostatic instrument in our coming discussion, but these instruments can also be classified based on their construction and application. Okay. So you have basically three different type of electrostatic instrument, out of which this attractive or attracted disc type of electrostatic tools are very much popular. Okay. So you have three types. You have attracted disc type, then you have quadrant electrometers, and you have multiplate or multicellular type of instrument. And you can see their construction, they differ in their construction completely. Okay. So let us talk about them in very brief, and let's conclude this discussion on different type of analog meters based on their construction. Okay. So as the name suggests, this attractive disc type electrostatic tool, you can see here you have two parallel metal disc. Okay. One is fixed and one is movable. Okay. They attract each other when a voltage is applied between them. Okay. So we will talk about them in more detail, so you can understand that, say this is basically based on kind of capacitive effect. We will talk about that in more detail. Okay. Then you have quadrant electrometers, where torque is produced due to the electrostatic force between charged quadrants and a suspended vane, okay, or say needle. Okay. Then the multicellular or multiplate type, you can simply see here you have moving plates and fixed plate. So it has a multiple set of fixed and moving plates, which increases the total electrostatic force, and the sensitivity of this instrument is much higher as compared to the two that you have just seen. Okay. And they are again used for high voltage application or some voltage, say like anything around till 20 kV or so. Okay. So we will see at least the attracted disc type electrostatic instrument. Okay. But this is in brief that how these instruments differ. Okay. So I hope that the classification of analog meters based on their construction is clear to you. We have discussed mostly on PMMC, moving iron, and the electrodynamometers. In the PMMC, we have seen that we have a permanent motor which looks like, say, which is kind of U shape, and you have a coil which is wound on a aluminum frame, and you have a core. Okay. And then how this current helps in producing a torque in this. Okay. In the moving iron kind of instrument, we have seen that you have a permanent coil. Okay. And there is a soft iron, and based on the current flowing through it, this iron is, say, getting attracted towards this, and because of which there is a movement in the pointer. Okay. In the other type, which is repulsive type of moving iron, we have seen that because of their repulsion between these two magnet, you have movement in this pointer. Okay. So that's why the first case was known as attractive type, because you can only have attraction here. Okay. There is no repulsion. But of course, for example, you can understand through repulsion also, but generally, I mean, you will find that this is only attraction, because this current flowing through this coil will magnetize it. Okay. and then you have attractive, repulsive, different kind of moving iron, and similarly we have seen other kind of tools which is or electrostatic tools which are very, very crucial for this course. Okay. So we will continue our discussion on the classification of analog instruments in our next class also. Thank you.